pick up where we left off. Last time we left off on 13. Remember, that was an ellipse, and we were looking for the number of points on the curve where we had horizontal tangent lines, which was 2. I'm curious, in your IB program, when you covered conic sections, did they cover only horizontal and vertical ellipses, or did they also cover translated or rotated ellipses?
Only horizontal and vertical.
Yeah, which most schools, that's all they cover. In 7 years, I've run into one student, and it wasn't an IB student, it was a regular honors pre-calc student who shows up one day and he wants to know how to do those. And that is tough, let me tell you. You end up having to rotate your axis by some angle and then translating all of your points based on that rotation. But it's very, very difficult to do that. All right. Number 14.
Okay. Wouldn't it just be A and D?
Yep.
Okay.
Now the one that you can't quite tell is F.
Right.
Theoretically, F could look like this, where the tangent line is flat. And that would be a 0 on the first derivative. It's whatever the slope of the tangent line is. But since they didn't put F down with A and D, we know that F does not have a horizontal tangent line.
Right.
Some functions would. If I graph this function right here, y equal x cubed, that looks like this. And that is a horizontal tangent line right there. This is probably your classic related rate problem. Did you have related rates last year?
Yes.
Okay. Let's draw this picture.
I mostly did it in my pre-calc class, though.
Okay. Well, that's very unusual. Most people don't get related rates in anything prior to calculus. It's actually probably the first part of calculus that starts being fairly difficult. Okay, this is a 13-foot ladder, so I know the hypotenuse is 13 feet. It's leaning against a 20-foot vertical wall, so that's 20. And the information they give to us is that the bottom of the ladder is sliding away from the bottom of the wall at a rate of 1/2 foot per second. What does that translate to? If I make that x, and this y, and this z, first of all, I know it's a right triangle, because walls are built at right angles. So when they tell me that this point right here is sliding in that direction at 1/2 foot per second, what does 1/2 foot per second translate to in terms of differentials? That's dx dt.
Right.
That's what that means, is dx dt is 1/2, and it's a positive 1/2. It's getting 1/2 foot bigger every second. It's not sliding closer to the wall, in which case it would be a negative 1/2. It's sliding away from the wall. Okay, well, what's the overall fundamental equation that I'm starting with here? What equation describes this triangle? Very fundamental. X squared. It's a right triangle. What's the Pythagorean theorem?
X squared plus y squared equals z squared.
So that's the fundamental equation. And the only information I have is a dx dt. So how do I get dx dt from this equation? You implicitly differentiate it.
Right.
Okay, with respect to t, which isn't even in this equation. So if I'm implicitly differentiating both sides with respect to dt, I got to do it to this side over here also. What's the left side become, okay? 2x what?
dx dt.
In other words, the rule when you're doing implicit differentiation is if you encounter any variable that is not this variable, you have to follow it with a d of that variable relative to t. In other words, it's essentially the application of the chain rule.
Right.
Okay? And plus what?
2y dy dt
equals
2z dz dt. China, are you doing all my math? Yes. Yes, she is.
Okay. So to determine the rate at which the top of the ladder is sliding down the vertical wall, well, that's dy dt, right? So that's what they're asking me to solve for, is dy dt.
Right.
When the tip of the ladder is exactly 5 feet above the ground. So
y would equal 5?
There's the 20-foot wall again. But now the conditions are slightly different. It's still a 13-foot ladder. When the tip of the ladder is exactly 5 feet above the ground, that's 5. What's x? That's your second basic Pythagorean triangle.
Right.
It's 5, 12, 13.
Right.
Okay. So I can figure out that they're talking about when this is 12 feet away from the wall. Now I have everything I need to solve for dy dt.
Okay.
Let me think for a moment. What's dz dt equal to? They didn't give us that. In other words, I can plug in everything here. If I plug into this equation, I've got 2 times 12 dx dt was given to us as 1/2 plus 2 times 5, that's what y is at the point they're asking, times dy dt, well, that's what we're trying to solve for. We know z is 13, so it's 2 times 13, but they didn't give us dz dt. Can we figure out what dz dt is?
I mean, isn't it constant, since the ladder will always stay constant?
So what's the change in dz dt?
There is no change.
0. In other words,
right.
dz dt is 0. Because it's a constant. It's not changing at all. Something
right.
not changing has a derivative that's 0. Okay, so if we do the math here, what do we get? 12 plus 10 dy dt equals 0. So dy dt looks to me like it's negative 6/5, which is an answer. Now, is that the proper sign? Should it be negative?
Yes.
Yeah, because it's sliding down. In other words, y is changing from bigger to smaller, and that's what makes it negative. It's not the direction. For a long time when I did these problems, I thought that the sign needed to be, well, if it's going down, it's negative. If it's going up, it's positive. If it's going to the right, it's positive. If it's going to the left, it's negative. But that's not the way it is with these problems. It's whether it's increasing or decreasing. That's what makes it positive or negative. Differential solving first, well, they're not even first order differential equations. This is a very specific set of differential equations that you can solve by a technique of separating the variable. Did you have this last year?
I don't think so.
Well, let's go through it. It's this one. We could have picked an easier one, but first of all, let's separate the variables. And by that, you can treat each of these differentials like a fraction. So I can essentially cross multiply here to get e to the y dy equals sine x dx. Okay, that step's pretty straightforward. Now, you can integrate both sides. What do I get when I integrate the left side?
It goes y e y.
No.
Oh, integrate.
So,
Integrate. Duh.
well, e to the x, its first derivative is the same as it is, e to the x.
Right.
Which means its integral is also e to the x. Because remember, the derivative of the integral has to equal the original function. So the integral of this is e to the y. What's the integral of the right side?
Cosine x?
Negative cosine
Right, negative.
x plus c.
Right.
Because these are indefinite integrals. Now, there's actually a plus c on the left also. But you combine all your c's into one c. I don't put c on the left and c on the right. I only need the c on the right. Okay? Now solving for y is a little tricky. Normally we would, in a simpler differential equation, we would have y equals this, and that would be our answer. But how do we get y?
Natural log?
Of both sides.
Right.
Take the natural log of that and the natural log of that. Natural log of the left is what?
Y.
And let's see, did they give us the answer yet? Yeah, it's natural log of minus cosine x plus c. And then they always, with these differential equations, they give you an initial condition. They say that y of pi over 4 is equal to 0. And this initial condition is always going to allow you to calculate what c is.
Right.
So let's do that. If I say y is equal to 0 when x is pi over 4, cosine of pi over 4 square root of 2 over 2. It's a positive. Positive square root of 2 over 2, but I still have the negative sign right there. In other words, I have that. So, what does this argument have to be for everything to be 0? In other words, for me to take the natural log of this number in parentheses and come up with 0, what does this thing in parentheses have to be?
The
natural log of what number is equal to 0? 1.
The natural log of 1.
1. Log of 1, no matter what base, is equal to 0. In other words, log base 7 of 1 is 0. Log base 10 of 1 is 0. Natural log of 1 is also 0. So, in other words, I need this to be 1 for this equation to be true. And so now I can solve for C.
Right. Would that make it B then? The answer B?
I'm sorry, what?
Would that make the answer B then?
Oh, well, I don't know yet. I haven't solved it. Let's add these two together. So now we know what C is. So now I can go up to the equation that I got and substitute what I have for C. So it's y equal natural log of minus cosine x plus 1 plus square root of 2 over 2. So we see that? Yep, you were way ahead of me. But that is the way. There's a very large order of differential equations that can be solved this way. Let's just take another one. Differential equations almost always start out with that. And let's say that it was equal to x over y. Well, if I separate variables and move the x's to the right and the y's to the left, I have y dy equals x dx. Process is to integrate both sides. That gives you y squared over 2 equals x squared over 2 plus c. And y is then equal to plus or minus the square root of x squared plus c over, or 2c. I think, if I did that right, yeah. And so that would be your answer. As long as you can separate the y's and the x's, you can use this technique, and it's actually pretty easy.
Okay.
Where differential equations is a course, an entire year-long course in college. And the reason being is that these kind of equations where you can actually separate the variables make up a very, very small percentage of differential equations. It's kind of like when you factor cubics by grouping.
Okay.
That's only maybe 2% of the cubics you come across. So that's not the only technique for factoring cubics. And that in itself is a course also almost. But if I wanted to separate the variables here, it was easy to do. But notice one thing. If I were to make it like that, I cannot separate the variables any longer. You see why? There's no way to get y on the left and x on the right.
Right.
If I subtract y to begin with, now when I multiply both sides by dx, now I got to multiply this dx by the y, the minus y. In other words, if I try doing this, now how do I separate the variables? Now I can't multiply both sides by dx. I'll have a dx next to this y. In other words, in order to use this technique that we went through there, you've got to be able to separate the variables. And it's not that easy to see what can be separated and what can't. I worked with these for a long time thinking, well, that sure looks like I should be able to separate it. but you can't do it. In other words, you need the x and the y to be multiplied or divided. If I had that, well, now I can separate the variables because I can divide both sides by y and multiply both sides by dx. So I end up with 1 over y dy, and over here I end up with x dx. Now you integrate both sides, and this becomes natural log of y equals x squared over 2 plus c. And then you do that same thing. Well, actually you do something a little different with that. This problem here is that now to solve for y, what would I do? In other words, when I get to this step, remember that when I'm solving differential equations, I want my answer to be y equals, not natural log of y equals.
Right.
How do I solve that for y?
If you multiply by, like, e to the x, would that multiply by e? Would the natural log cancel out, or am I thinking of something else?
It's called exponentiating, yeah. And in fact, it's very difficult to describe. I'm not sure exactly how to describe this with words. But what you essentially do is you take both sides and you make e the base. So you end up with e to the natural log of y equals e to the x squared over 2 plus c.
And then e in the natural log of y would cancel?
Is just
yeah, it would,
yes.
Yeah.
As long as this base here is the same as this number, then you get whatever is the argument. And so that's how you solve that. Now, this also gets a little tricky. Let's go through this while we're talking about it. So it looks like y is e to this, right?
Yes.
That's not actually the final answer. In other words, here's what you do on the right. You separate that into e to the x squared over 2 times e to the c. You see how I make that step?
Yes.
Well, now e to the c is just another c, right? In other words, because e is a constant.
Yes, and c is a constant.
E to the c into a big giant C, which means my final answer is not this plus c, it's c times that. So this is one differential equation that even though in the middle of solving it you add the c, by the time you're done with it, it's a multiplier.
Huh.
Yeah, it's pretty clever, but the key step here is this one right here. In other words, taking what you see there where the exponents are being added and separating that into two things being multiplied. Another bit of a tricky one. It's absolute value. And this whole thing is in parentheses. They want the area. Well, they want us to evaluate that integral. First of all, it's tough taking integrals of absolute values, right?
Right.
So what does this mean? What does the integral of this function mean? What does integral mean? Area under the curve.
The curve.
So.
But with the absolute value, it's not a curve, it's like a V?
Well, let's draw this curve. When x is 0, we have 2 minus 4, so we're at that point right there. It's a linear function. The key point is x equal 4, which at point y is 2. and it's linear, so it looks like this, and that v is upside down. The reason
Right.
it's upside down is because of the negative sign in front of the absolute value. And this is actually a little tricky to graph. Notice that it would have been real easy to think that we were making a vertical adjustment of +2. And maybe we did, now that I think about it. Yeah, we did do a vertical adjustment of +2. In other words, if I rewrite this thing as -4 minus x plus 2, well, it's the graph of that vertically shifted up by 2 units. Well, the graph of this thing is basically something that looks like that. In other words, when x is 4, we're on the 0 line. So it is the graph of the original absolute value function shifted up by 2. Now, the area of these two triangles is the answer to this integral, because this integral means the area under the curve. And it's important to note that this area is going to be negative.
Right.
Okay, so what is this area? This dimension is, that's at -2. And this comes when x is 2. And this comes when x is 4. And that value is +2. So what's the area of the left triangle?
Two?
It's the area, it's actually, we're going to
-2.
call it a -2 because it's below the x-axis. All areas
Right,
below the x-axis end up coming up negative. Okay, so we're going to, this is going to be positive. What's the area of this? This point over here is 6. Yeah.
Oh, okay.
Yeah, no, you're right.
Yeah, so 4.
So that's a +4. This is a -2. The net area is +2. The absolute area would be 6. In other words, if they said, what is the area of just the shaded regions, it's going to be 4 + 2. Because just like in geometry, you can't really have negative areas. It's a terminology problem is what it is. But whenever you write the integral of a function that is both above and below the x-axis, you're going to get an answer that is the net area, with all areas below the x-axis being negative, all areas above being positive. Okay? There is another way to do this problem, and that's to eliminate the absolute value signs and do it in 2 parts. In other words, I could eliminate the absolute value signs and integrate from 0 to 2 to get the lower left triangle, and then make it do the second integral from 2 to 6 of the different function. In other words, when I eliminate the absolute value sign, that changes that function. Except I would have to do it in 2 different pieces. I would actually have to do it from 0 to 4 and then from 4 to 6. Because from 4 to 6, that thing changes when you eliminate the absolute value. So let's separate this problem into 2 things. What's that integral?
1/2, like -1/2 cosine x squared?
Almost. You're close. Remember that when we take the derivative of our answer, it has to equal sine of 2x. Well, if you take the derivative of that, you get sine of 2x over 2 times the derivative of the inside, which is 2. So you do end up with sine of 2x. So this is the integral of the sine of 2x. And these are fairly straightforward when you have something like this. You just take the integral and divide by the derivative of the inside. Okay, so if I said, what's the integral of cosine of 5x? That's going to be sine of 5x divided by 5. Got it?
Yep.
Same thing with e. Same exact thing with e. If I want to take the integral of e to the 3x, that's e to the 3x divided by the derivative of the top, of the inside. So whenever you're doing these transcendental functions like this and you're taking integrals, it's not that hard. You just integrate it as if you would integrate sine of x and then divide by this coefficient. Now, whole different story if I put a square there. Then that becomes an unbelievably difficult integral to take. Okay, so as long as it's linear x, then you can do it. I think I've told you this before, but not all functions have antiderivatives. Here's one that does not have.
Yes.
There is no function whose derivative is equal to e to the minus x squared. And there's only one way to do that integral properly. And that's to turn this function into an infinite series and then integrate each term of the infinite series. So I can at best approximate the integral. I can clearly graph this function. And so surely there's an area under the curve. You know, if there's an area under the curve, there's got to be a way to find the integral of it. But this particular one this is Calc 3. You might get this kind of comes in the C section of Calc BC. And so you'll probably get into infinite series before you're done next year. All right, so let's see. We didn't finish it. The tough part is the second one. So what is the integral of 5 tan squared x cosecant squared of x dx? Well, I can certainly take the 5 out there. Let's do that.
Yes.
Just to simplify everything. Now, if only one of these things was the derivative of the other, I can just use the power rule. But it's not. So we need to use some trig identities. Usually when you have to use trig identities, convert everything to sine and cosine. So what does this all become?
Sine squared over cosine squared times 1 over cosine squared dx.
1 over sine squared.
Sine squared.
Always remember that when you're doing these, what do they call them? The reciprocal identities, that there's one co in every pair. And if you start out with tan, you know tan is 1 over cotan. And then the only question becomes, well, which does the secant go with sine or does the cosecant go with sine? Well, I need to have a co in every pair. So that's the way I remember it. There's my co in the bottom pair, there's my co in the top pair, there's my co in the top middle pair, and there's my co in the top pair. So secant can't go with sine. They wouldn't have a code. Okay? Now, sine squareds cancel. And now I'm trying to take the integral, 5 times the integral of 1 over cosine squared. Well, that would be tough, except what is 1 over cosine squared when you convert it back to a numerator trig function?
Secant.
Secant squared. And secant squared happens to be the derivative of what? Tangent.
Right.
I know, the derivatives of the trig functions are something that can leave you quickly. So this is a good review. But yeah, the derivative of tangent is secant squared. Which, which means the integral of secant squared is tangent. So there's plus 5 tan x plus c. There's our answer right there. In other words, that's the integral of this part. That's the integral of this part. I combine the c's from both into one c. And there's my answer. All right, let's see. I got to go to another page, 501. We're doing 19 here. Another tricky one. I told you they were going to get harder. Let's talk about integrating composite functions. In other words, if I wanted to integrate that integrates very easily. Forget 19 for a second. Let's just look at this one. The reason this integrates easily is because the derivative of the inside is cosine x, and it's on the numerator. And it's going to disappear when I turn this into a u substitution. In other words, let me show you how. If I'm going to integrate this by turning it into u substitution, my u is going to be sine x. Because I want to end up with u to the fifth. I know how to integrate u to the fifth. I don't know how to integrate sine to the fifth. Okay? Well, the first step you do when you do u substitution is you try to figure out what du dx is. Well, du dx is cosine x, which means du is cosine x dx, which means dx is du divided by cosine x. And what I'm going to attempt to do is to go in and substitute everything I can to turn this thing into an integral in u and not x. Well, I can do it because that becomes u to the fifth. I still got my cosine x, but notice now when I substitute for dx, I got du over cosine x. And you always end up with the derivative of your u variable in the denominator. And so now I can get rid of the cosine x's, and now I have a very easy integral to integrate. What's the integral of that?
Oh, 1/6 u to the 6th plus c.
And then I go back and I substitute sine x for u. So my answer ends up being sine to the sixth of x over 6 plus c. Okay? So whenever we see what looks like a tough integral, first thing you always want to check for is this the derivative of the inside of this? And if it is, we can essentially just use the power rule, and this thing's going to disappear. In other words, I would have a real hard time integrating that. Sine to the fifth of x, that would be tough to do. But once I stick the derivative of the inside next to it, like that, now it becomes very easy. So you're always looking for these. Well, notice, what would I let u be in the problem that we're looking at? In other words, if I decide to use Usubstitution, what's u going to be?
7 plus x to the 2/3?
Yep. 7, u equals 7 plus x to the 2/3. And the reason that makes such a terrific u is because the derivative of that leaves you with x to the minus 1/3.
Which would put it then in the denominator.
It's going to take out that x to the 1/3 there. Okay? I think. Yeah, let's see. Yeah, because I can... No, hold on. No? Let's go through it. So what's du dx? Let's see. It's 2/3 x to the minus 1/3, correct? Yeah, okay. This is going to work. So that when I go and solve for dx, I get du divided by this whole thing, which is the same as multiplying by the reciprocal. Like that. So that's what dx is it's, let me write it where the x is in a proper position. So when I solve for dx, just using algebra, I get this. And now when I rewrite this whole equation, I've got u to the fifth times 3/2 x to the 1/3 du. And I still have my x to the 1/3 in the denominator, which now cancels out with this x to the 1/3. Again, I have a simple integral in u. Now, you cannot integrate an integral in u if you have any x's in there. This only works because I'm able to cancel the x's and completely turn it into an integral in u. You can't always do that. So those problems you can't use Usubstitution. But always look for this. Is the derivative of the inside in my numerator or denominator? And yes, it is. Perfect. Because the derivative of the inside is going to end up in the denominator. In other words, that x to the minus 1/3 that you get ends up down here, canceling out with the x to the 1/3.
Right.
And then you just go back to finish solving it. You go back and you substitute 7 plus x to the 2/3 for u after you've taken the integral of u to the fifth, and you get your answer. And in fact, can we guess what it has to be here? Has to be this a. In other words, the integral, oh no, there's a 3/2. Yeah, there's a 3/2 that I have to multiply everything by. So So it's u to the 6 divided by 6 with a 3/2 out there, which is 4. So I'm going to be multiplying everything by this. This is the correct answer right here. All right. 20. I got ahead of myself when I gave you the example. That's exactly the example I gave you. In other words, we're looking at a situation where the derivative of this is the derivative of the inside is cosine x. We know that derivative will end up in the denominator taking out that cosine x. So I don't even have to go through the Usubstitution here, because all I have to do is use the power rule on that. In other words, the answer is the sine to the 5th of x divided by 5 plus c. In other words, I can go straight to the power rule as long as I am looking at that. As long as I am looking at a composite function where the derivative of the inside is next to it. Hold on 1 second. I hear my dog yelping. 1 minute. 1 minute. Bye. Bye. Sorry about that. I'm worse than a mother hen with my dog. All right. Did you get the fundamental theorem of calculus last year?
No, doesn't sound familiar.
Okay. Let me give it to you real quick, because you'll get it for sure. And it's not that hard. This makes it a little harder than it appears to be. If you take the derivative of an integral, with respect to x, in other words, if the integral's limits of integration go from a constant, and it doesn't matter what this constant is, to x, and you take the derivative of that function, you get f of x. As you would expect, if you take the derivative of an integral, you should get the function, right? Because
Right.
the integral goes one way, the derivative goes in the other way, the derivative of an integral should be the function. And you do. That's part one of the theorem of calculus.
Okay.
That's the most important theorem in all of calculus, without doubt. And in fact, in my textbooks, it says it might be one of the most important theorems in all of math. That's how important this theorem is. Part two is the integral from a to b of f of x dx is equal to the antiderivative of the function evaluated at b minus the antiderivative of the function evaluated at a.
Now that looks familiar.
Yeah, you knew this. In other words, that's the way we do it. If it's x squared, we're going to take the antiderivative of it, we're going to evaluate it at b, and then subtract the evaluation at a. So this is perhaps the most important part of the fundamental theorem of calculus, is the second part. That's the part we use all the time. But that's the easy part. The first part's a little more difficult. Now, if this said t instead of t to the fourth, then all I would do is substitute the t for the x, and my answer is e to the t squared. It's that simple. When this is exponentiated, then you have to apply the chain rule. In other words, I'm going to substitute t to the fourth for x, so my answer starts out as e to the t to the fourth squared, but then I have to multiply it by the derivative of that, which is 4t cubed. And so my final answer is e to the t to the eighth times 4t cubed. D. If you make this x squared instead of x, then you just plug in x squared wherever you see x, and you multiply the final answer by the derivative of x squared. Okay? Now, the other key part of this definition is it doesn't matter what a is. If I said, what is the derivative of, and it also doesn't matter what this variable is. This is what they call a dummy variable, the t. Why? Because it doesn't matter what it is, it's always going to turn into x squared. This is x squared. This is the answer. If I take the derivative of t squared from a to x, I just substitute x for t, change the whole thing to a function in x. And it doesn't matter if a is negative, 0, or a billion. If you go to some constant to x, then you can just substitute the x into whatever the variable is in the function you're dealing with. All right, let's see if we can get one more in here. At least one more. All right. How many chain rules are we going to have to apply in this problem? That's always the toughest part of the chain rule. Chain rule is pretty easy when you just have to apply it once. But when you have to apply it multiple times, it becomes a little tricky. And the way to figure it out is, what would you let u be? In other words, to really figure out the chain rule, you want to figure out what you would let u be. If I let u be that, then I'm going to have u to the fifth. I can easily differentiate u to the fifth. Okay? But then I would have to multiply it by du dx also. In other words, by the derivative of the inside. Well, there's one more inside. In other words, this was the first inside. This is the second inside.
Right.
So, we're going to multiply, we're going to use the power rule, and then we're going to multiply by the derivative of that, and then we're going to multiply that by the derivative of that. So, let's see, let's start with the power rule. 5, and I'm going to go ahead and, I'm not going to use u, I'm going to spell everything out. So that's the power rule. And that's the derivative of the outside.
Right.
Now, to figure out what du dx is, in other words, I have to multiply this whole thing by du dx. So let's go up to this and figure out what du dx is. Well, what's the derivative of the arc cosine? It's It's 1 over, actually it's the derivative of the inside divided by 1 minus the square root of 1 minus x squared. Okay? But in this case, it's going to be negative. It's negative also. So it's negative 2x divided by the derivative of 1 minus x to the fourth. You see how I got du dx?
Yes.
Okay. In other words, I had to apply the chain rule to this also. And notice that instead of x squared down here, I had to substitute x squared for x, and so I got x to the fourth in the denominator. And my numerator comes from 2x, which is the derivative of this last inside. And the negative sign comes from the fact that the derivative of the arc cosine of x is negative 1 over square root of 1 minus x squared. These, it's worth noting, incidentally, that when you take the derivative of an inverse trig function, you get a polynomial. You don't get a trig function. And keep that in mind. That's going to become very important for doing the harder types of integration. Is that when you have, in other words, no matter whether we're taking the derivative of arc tangent, arc cosine, or arc sine, we get a polynomial that looks something like, 1 over square root of 1 minus x squared. And yet we're taking the derivative of a trig, but it's an inverse function. So that makes sense. It's not the trig function. All derivatives of trig functions are trig functions. But derivative of inverse trig functions are polynomials. So remember that when we get along about mid-year next year, you're going to have to take the integral of that. Well, guess what that is? That's arc cosine. In other words, if the derivative of arc cosine is this, then the integral of this is arc cosine. And you end up getting lots and lots of very complicated functions that kind of have an appearance like that, or something like this, and so you end up using either arc cosine, arc tangent, or arc sine to integrate them. All right. You will find that if you multiply this, the derivative of the outside, times this, the derivative of the second inside, and the derivative of the third inside, or the first and the second, you will get minus 10, because the minus 2 times the 5 gives you minus 10, x arc cosine squared to the fourth, and that goes in the denominator. It's not this one, though. It is this one right here. In other words, we need a square root of 1 minus x to the fourth in the denominator. That's a hard one. This is probably one of the harder applications of the chain rule that I've seen. Okay, good place to stop. We're getting 10 to 12 of these questions done each session, which is, and I think these are pretty good summary of what, if you haven't had it already, you will have this stuff, clearly. This is the Calc AB exam, so everything on this you'll certainly need to know. At which point in time, I don't know. I'm not sure where they're going to start you out on Calc BC. I've had quite a few Calc BC students, but I usually get them by November, so I'm not quite sure where they start in August. So I will talk to you next time, Diana.
All right, thank you.
All right, bye-bye.
Bye.